Welcome class to our video notes lesson on section 5.3, where we are going to learn how to graph cube root functions. Now before we get into how to graph their HK versions, we will spend some time to learn about what we call the parent function, which is just the plain cube root of x. So we call it the parent function because one, it's the simplest form of a cube root function. But two, it will determine the shape of all other functions that are in HK form that contain cube roots. So these HK versions will have the same shape that was determined by the parent function, but maybe have some transformations to them. Okay, so let's start by looking at just the plain cube root of x. So because the y value for this function is going to have to cube the x value, I want to be really careful as to what types of values I plug in here for x. I want them to be numbers that are easy to take a cube root of. So I want them to be perfect cubes. Okay, and simple ones, not super advanced ones. So maybe I'll start with 0. I'm going to put that one in the middle here because I know that the cube root of 0 is just 0 because 0 times 0 times 0 equals 0. And then 1 is a simple perfect cube. I know that the cube root of 1 is equal to 1, right? Because 1 times 1 times 1 equals itself. So its cube root is 1. But then aside from these two, I might look at a number like 8. Because the cube root of 8 is 2. Because 8 can be broken into 3 factors of 2. And if you remember, when you're taking a cube root, you have to have 3 identical factors to be able to evaluate that cube root. So because the cube root of 8 is 2, then 8 is a good number to plug in for x. But I also should plug in a few negatives also, so that I get a full idea of what the shape of this graph looks like. So I'm going to go ahead and use these same perfect cubes, but the negative versions of them, -1 and -8. Because if I cube root -1, I get back -1 for the same reason that I get 1 when I cube root +1. Because if you multiply -1 times -1 times -1, the first two negatives will cancel and give me +1. But when I take that +1 and multiply it by the leftover -1, I get a result of -1. So the cube root of -1 is equal to -1. A similar thing happens when I take the cube root of -8. It's going to equal -2 for a similar reason. If I multiply -2 times -2 times -2, the first two negatives cancel and give me +4. And then that positive combined with that third negative would give me -8. Therefore, the 3 numbers that multiply together to equal -8 are -2, -2, -2. So the cube root of -8 is -2. So I want to make a comment here, just really quick, about what just happened here, is that it is possible and okay to take the cube root of a negative number. It is okay and possible to take the cube root of a negative number. We just did it here. We just took the cube root of -1 and we just took the cube root of -8. Now the reason why it's possible to do that is because when you multiply a negative number to itself 3 times, right? This is a cube root. What does it mean to take a cube root or a third root? Is you need that factor 3 times. So when you multiply a negative number to itself 3 times, the result is negative. So it is okay, therefore, to take a cube root of a negative. So what does that mean? That means the domain for this function, which is the set of all inputs, by the way, it's all the types of x's that you're allowed to plug in, is going to include all real numbers. That's what this fancy R stands for. It stands for all real numbers. And what does that mean? That means every single x value from -infinity all the way to +infinity on the x-axis Every single one of those is fair game to plug into this cube root. So that's why we also sometimes write this in interval notation, and we say all x's from negative infinity, right, that spans all the way from the left all the way to the right, is fair game for this domain, because I can take the cube roots of negatives. I can take the cube roots of positives too. I can take the cube roots of fractions. I can take the cube root of any type of number. But then because when you take the cube root of a negative, the result is also negative, then the range is also going to equal all real numbers. Or I can say from negative infinity to infinity, because when you multiply that negative number to itself 3 times, or let me put it this way, you'd have to multiply a negative 3 times to result in a negative, right? So the output, the cube root, would have to be negative as well. So that's one of the things I actually like about cube roots, is that you don't have to worry about that even, odd rule from before, because it's okay to plug a negative in, and when you do, a negative will come out, no big deal. You don't have to choose, is it positive, is it negative? It's got to be negative. So it's very easy to evaluate these as long as I plug in nice perfect cubes. Okay, so let's go ahead and plot these points, and then we can kind of answer the rest of these. So I'll plug the point here, -8, -2, and then -1, -1. We have the point 0, 0, +1, +1, and then +8, +2. So we get a graph that kind of looks like this here. So we had a graph similar to this back in Unit 2. We called it the lazy S, or I think we called it the squiggle or the snake or something like that. But this one will be called, I'm going to call it the sideways squiggle, for lack of a better name. It's the sideways version of that graph back in Unit 2. In fact, let's just kind of briefly remember. So back in Unit 2, we learned about the y equals x to the third function, where we were taking our x values and then cubing them. So we were going backwards. We were taking numbers like 2 and then saying, okay, 2 times 2 times 2 is 8. So we had the point 2, 8 instead of 8, 2. And then taking the numbers like 0 and cubing it and saying, okay, 0 times 0 times 0 is 0. So we had this point. We had 1, 1, -1, 1, and -2, -8. So we had this squiggle graph, or lazy S we called it, back in Unit 2. The y equals x cubed graph. So this really is just the sideways version of that. It's the same points, -2, -8, -1, 1, in reverse. It's just kind of the reverse order of y equals x cubed. So the graph has a similar look to it, only it's going right and left instead of up and down. So sometimes it helps to think of it as the reverse order of y equals x cubed. So now let's look at the equation here, how this parent function equation compares to the AHK version. So notice in the parent function, we just have the cube root of x, right? Well, that means that the a value must be 1. In order for there to even be a cube root there, it must be being multiplied by 1. So then the a value for the parent function is 1. Now notice in the parent function, there's nothing inside the cube root. So that means that h is 0. And then there's nothing being added here. So then that means that my k value would be 0. So for the parent function, we would say that a is 1, h is 0, and k is 0. So right here for hk, for the parent function, it's centered right here at the origin, right here at 0, 0. Now that won't always be the case for the hk versions, right? Because some of them are going to move away from the origin. But for the parent function, it's always centered right there at the origin. So what does that mean? That means that the x and y-intercept end up in the same spot, right in the middle, because that's right where it crosses both the x and the y-axis, is right at that hk point, 0, 0. We already mentioned the domain is all real numbers and the range is all real numbers. Now for increasing, remember that's when we read the graph going from left to right, so from negative infinity toward the right, positive infinity, and we ask ourselves if the y values are going up or down. Well, if you look at this function, they're going up the entire time. Granted, not very fast, but they're still increasing the whole time. So we would say that this graph is increasing from all the way from negative infinity to positive infinity. Basically, for the entire length of the x-axis, as you move to the right, the graph goes up. So then what does that mean for decreasing? That just means it never will decrease, at least not the parent function, right? We'd have to have some sort of reflection over the x-axis to make it decrease. So for the parent function, it's only ever increasing. Now, is it one-to-one? Yes. What does it mean to be one-to-one? It means that for every x value, you only have one y, and vice versa. And you can kind of see here with these examples of like negative, for example. If I'm taking a cube root of -8, that could only be -2, because you'd have to multiply -2 to itself 3 times to get -8. So there's only one possible answer you could get for y when you plug in -8 for x. And vice versa, if you're getting a y value that's negative, -2, there's only one possible thing we could have plugged into that root to get the negative answer. So there really is only one x for each y and only one y for each x. So yes, this function is definitely one-to-one. And since the parent function is one-to-one, all the other cube root functions are going to be one-to-one as well. And then there is no minimum or maximum on these cube root functions because of the fact that they only ever go in one direction. There's never a point where they sort of turn around and go the other way, creating some type of min or max. So there just really won't be any for these cube root functions. So now that we've learned a little bit about the parent, let's remind ourselves some of the things we have to do to make the transformations, and then we can start graphing transformations of this function. So recall that when the a value is less than 0, is negative, that will create what we call a vertical reflection on the graph. That'll sort of make your parent function sort of look like this. So if you look at the parent function, it goes up from left to right. But if I were to reflect that, it would look something like this. So that's what happens when the a value is negative. Now, if the absolute value of a is less than 1, which by the way, that means that a would be in between -1 and 1. So if a is some number between -1 and 1, so that if I absolute valued it, it would be some positive number less than 1, that'll create a vertical compression, or we could call that a shrink. Because remember, the a value is getting multiplied to the y coordinate. The a value multiplies to the y coordinate. So if I'm multiplying some number less than 1 to a y value, it's going to shrink it and cause it to become smaller. And then on the other hand, if the absolute value of a is greater than 1, so that means that a is either greater than 1 or less than -1. Because if I absolute valued a number less than -1, like -3, for example, if I absolute valued it, it would become +3, which is now greater than 1. So remember, the sign doesn't shrink, doesn't compress. It's the sign will reflect it. If a is negative, it reflects it. But if a is some number between -1 and 1, that's what shrinks it. If a is a number greater than 1 or less than -1, that creates what's called a vertical stretch. Because I'd be taking a number like 2, 3, 4 and multiplying it to the y coordinate, which will make that value bigger and cause it to stretch vertically. Vertically because it's the y value that's getting bigger. So that's what a does. A has a lot of power because of the fact that it's multiplying to the y coordinate. Now h adds to the x value. It adds to the x coordinate. So it has the power to shift the graph horizontally. So it creates this horizontal shift. Horizontal because it's affecting x, not y. But there's something super important that you have to remember about h, and that is that h is always opposite from what you see in the equation. Because remember, in the hk form of the equation, the h is coming after a subtraction. And so if h is positive, then you're going to see x minus a number. If h were negative, it would turn it positive. It would look like x plus a number. And so you have to just kind of consciously remember that h is always the opposite sign from what you see in the equation. So once you've determined what h is, the graph is either going to go left if h is negative, or right if h is positive. And then the k value, so this will add to the y-coordinate. So again, because it's simply adding and not multiplying, it has the power to shift. It'll move the graph around a little bit. It can't really change the shape though, right? It can't shrink or stretch or reflect. That would only happen through multiplication. But since k is adding to the y-coordinate, and it causes a vertical shift. Vertical because it's adding to the y-coordinate. The graph will go up if k is positive and down if k is negative. So that's how these values affect the shape of the graph. Now, in order to graph the function, these are the steps here. So basically what we first always do is identify the parent function, which for this section, right, for section 5.3 is the cube root function. It's the y equals the cube root of x. So we have to identify that first. And then we either recall or make a table of values for that parent function so that we know what the shape of our new graph is going to look like. Now, when we're doing that, especially for cube root functions and square root functions, we want to plug in x values that make sense, that are easy to evaluate. So again, for this section where we're working with cube roots, we would want to plug in x's that are perfect cubes. X's like 8 or 1 or -8, -1, numbers that you can easily find the cube root of. But when we're graphing in HK form, after we've figured out the parent, we then need to identify a, h, and k. And we make a new table of values using the rules, right? You add h to the x coordinate, you multiply a to y, and you add k to y. Then we graph our new points and then find the new defining characteristics, which would be these things up here. So let's try that on the second page. Okay, so here in example 2, here is our equation in HK form. And what we're supposed to do first is identify the parent function, which in this unit will be challenging because you just learned a section on square roots, and there's just one minor subtle nuance between square roots and cube roots in the way they're written. And it's just this little teeny index right here. You've really got to pay attention to the index, which here is telling me, okay, my parent function is a cube root, a third root, not a square root. That makes a big difference when I'm deciding what kind of points I can plug in for x. Because remember, for a cube root, I can plug in negatives. In fact, I should plug in negatives so I can see the full shape of the graph. Okay, so I've identified my parent function as the cube root. I've plugged in numbers that I can easily take the cube root of. I've plugged in a few positives and a few negatives because I can, therefore I should. And then I take their cube roots to get my y values. So what I have here are the points for the parent function. Now what I'm going to do is come back to this equation and say, well, what is different about this equation from the parent function? Well, I can see that I have an a value of 4, right? This is an a value of 1, but this equation has an a value of 4. So that is going to create a vertical stretch. This graph is going to look much more stretched than the parent function does. I look inside my cube root, I don't see anything there. That means h is 0. So h is always the thing that sort of happens inside the function with x. If nothing's underneath that cube root, that means h is 0. Then I notice there's a number being subtracted after the cube root. That would be my k value of -5. So since I have a k value of -5, that means that my graph is going to shift down 5 units. Down, it's a vertical shift because it's the k value, not the h value. Okay, so just from remembering what the parent function looks like and noticing that now my h and k, right, is 0, negative 5. I'm going to fill that in here. My h and k is 0, negative 5, which, by the way, is like the center or the middle of the squiggle. In fact, let's just take a peek at that parent function really quick. See, this is 0, 0, and the parent function is sort of right where that concavity changes. You could think of it as a inflection point, or you could think of it as a point of symmetry, but it represents that middle point of the graph. That's the parent function. Now for this function, that's going to be 0, negative 5. So that's right here. So that's going to be where that change in concavity happens, and there's going to be a stretch. So I'm thinking the graph's going to look something like this. A stretched out version of the squiggle that is now centered at 0, negative 5. Of course, I need to get my actual points and figure out where it actually goes, but I'm kind of just going to draw that in there so I can have an idea of what my answer should look like. Okay, so now we're going to follow the transformation rules. So I'm going to make a column. Well, my x's are going to stay the same because their h is 0, so that doesn't change. So I'll still have negative 8, negative 1, 0, 1, 8. But for the y values, you remember we multiply a to y, so it's going to be 4 times y, and then we add k to y. Of course, k is negative, so we'll subtract. But when I say y, I mean these values here, the negative 2, negative 1, 0, 1, and 2. I'm going to multiply each of those by 4 and subtract 5. So let me write this down here so I can see my final values here. So I still have my same x's. So this will become negative 8 minus 5, which is negative 13. Negative 4 minus 5 is negative 9. 0 minus 5 is negative 5. 4 minus 5 is negative 1. And then 8 minus 5 is 3. So these are the points I'm going to plot over here. But I want you to notice something, that my middle point became 0, negative 5, which is what should happen, right? The middle point should match hk. When I say middle point, I mean that original 0, 0 from the parent function should now become hk. So let's graph our points here. So I have negative 8, negative 13. So this ends at negative 10, but I'll add in an 11, a 12, and a 13. So negative 8, negative 13 would be like right here. Negative 1, negative 9 would be right about there. Then I have my point 0, negative 5. 1, negative 1, and 8, 3. So this graph was actually much more stretched, even more than I did. It was an even more exaggerated stretch than what I wrote in, because it was quite an extreme stretch, stretching it by 4, a multiple of 4. And you know, when you're given the a value, you can see that between the middle point and then the next point right after that, you can see that change of 4 right there. That's a good one to kind of gauge your a value to see if you did it right. And you can see that this point is 4 units higher than that middle point. Of course, that slope doesn't continue, right? This doesn't have a constant slope of 4. The next point is like way different. It's over here. But the very first one, you should see that change of 4 between the first point and the middle point. It's a good way to check. So there is our finalized graph here. So notice that the domain is still all real numbers. It still spans all the way from the left of the x all the way to the right. You can write that in interval notation, because the graph is allowed, so from the center, the graph is allowed to go left, right, up, and down, right? So my domain and range is all real numbers for both. And I'll put the interval notation on here as well. And this graph, because the a value is positive, this graph is increasing the entire time. From all the way from the negative part of the x-axis to the positive part. As it moves to the right, the y values are ever slightly going up that entire time. They are not going down. So there is no decreasing interval for this function. Yes, this function is one-to-one, meaning it has one unique y for each x and one unique x for each y. So it works both ways. There is no maximum or minimum for this function because it never changed direction. It just always only ever went up. So it never turned around, creating a max or a min. Then for the y-intercept, this is what we do to find the y-intercept, is we plug N0 for x. I really hope you guys write that on your outline because that's what you do whenever you're trying to find a y-intercept that isn't obvious. I do realize that this one is obvious. It's -5. But I want to show you how to find it. So you plug in 0 for x. So in this case, I would have 4 times the cube root of 0 and then -5, which would be 4 times 0, because cube root of 0 is 0, -5, and then 4 times 0 is 0. So 0 minus 5 is -5. So if we weren't able to see it off the graph, which I can, I could do it this way. Plug in 0 for x, solve for y. Remember to write your intercepts as ordered pairs. So 0 for x, -5 for y. Now for the x-intercept, I want you to put a star by this because you're not really technically able to do this one yet. This is coming next unit. We will learn how to solve these. But this is what you would do. You would plug in 0 for y and then solve for x. So it would look something like this. Where the f of x is over here, this is also thought of as y. You could plug 0 in for that, and then you would have to solve this equation for x. And we're going to teach you how to do that next unit. So for now, we can kind of look at the graph and sort of estimate. It looks like it's crossing somewhere between 2 and 3. So maybe I'll say, okay, it looks like it's approximately at, I don't know, it looks like maybe 2.3. So we could maybe just say, okay, approximately 2.3, 0 for now. For now, okay? Once we get to unit 6, we're going to want you to be able to solve this equation and tell us exactly what it is. But we'll save that for next unit. Okay, so then in number 3, again, when you come across an equation like this, you need to identify what the parent function is. And especially now that we're going to have a combination of root functions, square root and cube root, you really need to pay attention to the index to tell yourself, okay, this is not a square root, this is a cube root parent function. So when I'm deciding what x's to plug in, I want to pick x's that are perfect cubes, and that means I can plug in negatives. So I'm just going to use the same x's that I used in my last parent function, and I'm going to use the same y's because we just did this table, so it's okay to kind of use those same values. Okay, but then I'm going to recognize that I have some transformations here. I've got a -1 in front of the cube root. That means my a value is -1. That means my graph is going to have a vertical reflection. Okay, it's going to kind of go down from left to right instead of up because of a vertical reflection. Then I do see a number inside the radical this time, and I have to remember that h is opposite from the equation, so h is -2. Because remember, in the hk form, it comes after a negative, so this would have really been x minus -2 minus 7, right? And then that's how it became positive, because I was subtracting a negative, so h is negative. Meanwhile, the k is just -7 because it's whatever is being added or subtracted after the cube root. So we've identified our a, our h, and our k. And because h is -2, that means I'm going to have a shift that's going to go to the left 2 units, right? It's horizontal because it's adding to the h, so it's going left. And then because my k is negative, my graph is going to go down 7 units. Since it's adding to the y-coordinate, it creates a vertical shift, so it's down 7. This one was left 2. So if I were to just sort of eyeball this graph, I know that my hk, my middle point, is at -2, 7. Right? That's going to be right where that point of symmetry is, or that inflection point is. Let me sketch that out. -2, -7. And then from there, it's going to have this vertical reflection. So instead of going up like the parent function does, it's going to kind of go down like this, right? Because the parent function kind of looks like this. So if you reflect this top part down and this down part up, it looks like that. So it's the same kind of shape here, but left 2 and down 7. So again, I need to get the actual points. I can't just say that that's my graph, but I'm going to sketch this here to give myself an idea if I'm doing it right when I sketch my new points. Okay, so let's get our table of values for the transformed function. So for the transformed function, I'm going to do x minus 2. So remember, what happens to x in my table is opposite what's happening to x in the equation. And then I'm going to do negative 1 times y minus 7. So my x's were these ones here. So these are the numbers I'm going to subtract 2 from. And then for the y values, that were these here, the negative 2 through 2. I'm going to multiply all of those by negative 1 and then subtract 7. So you can see when I multiply them by negative 1, that's what makes their signs change, which is what makes them reflect over either above or below the x-axis. So let me write my finalized points here so I can see what they are. So this would be negative 10, negative 3, negative 2, negative 1, and 6. And then here I'd have positive 2 minus 7, that's negative 5. Positive 1 minus 7, negative 6. 0 minus 7, negative 7. Negative 1 minus 7 is negative 8, and then negative 2 minus 7 is negative 9. So notice in my table, the middle point ended up being hk, which is what should always happen. The point that was originally 0, 0 from the parent function should turn into hk from your equation. Okay, so now let's plot these points and see how we did. So negative 10, negative 5 would be like right here. Negative 3, negative 6. Wow, that's pretty good. Negative 2, negative 7, of course we did already. And then negative 1, negative 8 right there. And 6, negative 9. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Wow, okay. That's pretty eerie how close my sketch was there. But it looks almost spot on to the actual transform function because you can kind of get an idea just by knowing these changes. Vertical reflection, left 2, down 7. These points also did the same thing. So you can see the domain, again, is all real numbers. I'll put the interval notation for that as well. And so is the range. They always will be for a cube root function because your function's allowed to have negative and positive inputs and outputs. Now this time, because the a value was negative, right, it was negative 1, this graph is no longer increasing. Look, as x goes to the right from negative infinity to positive infinity, the y values go down that whole time. So this function decreases the entire time as x goes from negative infinity to positive infinity. Yes, the function is 1 to 1. All cube root functions will be no min or max because cube root functions never change direction. They only increase or decrease. So there's never a min or a max. This one was decreasing because a was negative. For the y-intercept, we plug in 0 for x to see what y equals. So let me do that down here. So what I'm going to do is I'm going to take 0 and plug it in for x in my cube root equation. So then I get negative 1 times the cube root of 2 minus 7. Now the cube root of 2 is some decimal, so I'd rather you not give me the decimal and just leave it like this, negative cube root of 2 minus 7. Like just leave that as your y value because I can see here it must be some number below negative 8. It must be, you know, negative 8 point something. But that would be an approximation, whereas this is the exact value. So I'd rather you leave your answers in exact value. So it was 0 for x, and then the negative cube root of 2 minus 7 for y. That would be my y-intercept, which, yes, is approximately negative 8 point something, but I'd rather you give me the exact value. Now for the x-intercept on this one, it's going to be like, this graph's going slowly like this. It's going to be somewhere way down the negative side of the x-axis. So again, we really can't tell from the graph, and we have to be able to solve this equation. But let me show you what the equation would be. So again, for x-intercepts, we plug in 0 for y, and then we solve for x. So in this situation, I would be plugging in 0 for y, and I would have negative 1 times the cube root of x plus 2 minus 7. I would then add the 7 to the other side. I would divide both sides by -1. I would raise both sides to the third power and then subtract 2 from both sides. So I would end up with this insanely large negative x-intercept, which again, I went through that quickly because you don't really need to know that part yet. This is coming up in our next unit. In Unit 6, you will learn how to solve all these types of equations, and at that point we will require you to be able to find these x-intercepts. For now, you could just say, I'm not sure. Or if you can see it on the graph, you can estimate it. For this one, I'll go ahead and put it in here since I did figure out what it was. So it's -345, some really large negative. But for your homework and quizzes and tests, you can either estimate off the graph or just say not sure yet. But that will conclude our video on 5.3, and I can't wait to practice these with you in class. I'll see you there.